Welcome back to the UGC lecture series on laser physics. In the last lecture, I have been touching upon the beginning and the importance of dye solution lasers. We shall continue more about the description, its special behavior, in what way it is important. As I told you earlier, dye solution is a pigment kept in suitable solvent like alcohol or water. These are the two most common liquid media. They are the two common solvents. This is kept in a, just imagine the same ruby rod, remove the rod, put a tube made of quartz. I repeat, take the ruby rod in the same experimental setup, design setup, have a quartz tube in which you can keep the dye solution. Then again, using the same kind of flash lamp, you can produce population inversion in this dye solution media. The dye solution media means the solvent acting as a media to disperse, separate out the molecules of dye. That is all what is doing. In addition, it is giving a cooling also. What is active is the dye molecule. One such dye molecule is the rhodamine 6G, which I have already touched upon, and this has a strong absorption and emission characteristics because it has a strange and special property of a pi electron, which can be easily delocalized. Delocalized means it can be pushed from one end to another end. When it is at some point and when the radiation comes, ultraviolet light, visible light comes, the molecule gets excited, means it is absorbing the radiation and allows the pi electron cloud to move from one end to another end. Since the pi electron cloud can be pushed here and there, the absorption characteristics is very high. Since absorption characteristics is very high, it can take a lot of energy from the external sources. Second point, since the molecular structure is rigid, it can re-emit in the form of a useful fluorescence or emission. As I mentioned earlier, the fluorescence efficiency is 0.8 or even 0.9. which means if we give 100 photons, if the dye molecule R6G absorbs 100 photons at the wavelength of visible region or in the green region, it will re-emit in the orange color with 60 photons. That means fluorescence efficiency is 60%, 70%, sometime in a proper environment it can even go to 90%. Such an efficient dye molecule, since they emit efficiently, they have a high optical gain. Since they have a high optical gain, you can have even a small length for resonator, small length for active medium. That means a ruby rod needs a minimum of 5 centimeter, 10 centimeter length, whereas the dye solution can have in a small tube of 5 millimeter. Even then it will work. Later I would touch upon the pumping source for the dye solution. There are two very good sources. One is a nitrogen laser, other is an excimer laser. When we employ these kind of gases, gas lasers to pump dye solutions, dye solution can have an active medium length of even 1 millimeter or even less. Even then it is capable of producing laser action. That is first property, that is optical gain is very high for dye solution. What is furthermore fascinating about dye solution is they have a broad absorption and emission band. I have shown you that. On the right hand side you have the absorption profile and the emission profile both are very broad, of the order of 30 to 40 nanometer. This is because dye is a complex organic molecule with a large number of vibrational energy within the electronic energy level. On the left hand side, you see the energy level of a dye molecule like rhodamine. The lowest one is called S0, next higher energy is called S1, more is S2. All these are electronic energy level. These are called singlet electron energy level. This is because the molecule contains usually even electrons, even number of pi electrons. Since even number of p electrons are there, the ground state will be usually a single state. So, you have single state, the lowest single state we call this S0, higher one S1, higher to S2, like that. Not only that, it has a triplet state also. In the triplet state, you have the triplet state. The difference between single state and triplet state is, in the triplet state, the spin, since we got 2 electrons, in singlet the spins are anti-parallel, half and another half, the total spin is 0, that is why we get a singlet state. Whereas, in the triplet state, both have same spin, half and another half, half and another half, total spin is 1. When we have a spin 1, the multiplicity is 3, 2s plus 1 is the rule. Triplet, you have the triplet state. The triplet state will have a energy slightly lower than the singlet state. This is the rule in molecular spectroscopy. Because of this one, all the molecules which go to S1 state will come down to the lowest vibration level of S1 state very quickly, within a few picoseconds. From there, they will get transferred to triplet state in about 10 or 20 nanoseconds. In the triplet state, they stay for a long time, for about 20 seconds or even 20, sometimes 20 milliseconds, sometime in 20 microseconds, sometime even in 20 seconds. It depends on the environment, if it is in a solid state or if it is a lower temperature. There are so many situations. Usually, the triplet state is a metastable state with a long lifetime. Suppose we flow the dye solution very fast, then there will be more and more collision, cooling temperature, all this. Because of this, the triplet state will get quenched and will come back to S0 state. Let us not bother about the triplet state for the time being. Now, let us focus at this stage among the singlet states. The lowest singlet state, S0, has certain vibration levels, a set of vibration levels. Now, S1 also has certain set of vibration levels. Then what could happen is, if we can imagine that S0 is a ground state level, S1 is a pump level, then the lowest vibration level of S1 is the upper laser level, and the upper vibration level of S0 is a lower laser level. You have a 4 level energy state, 4 distinct energy levels. This is an essential condition for continuous laser action, and if we could run it, flow it, cool it, then you will have a fresh solution of dye molecule in this 4 level scheme. So, you can have a continuous laser action. You can continuously excite this dye molecule using an argon ion laser, about which we will see later, an argon ion laser. So, you can get a continuous wave laser from a dye solution. That is the biggest advantage. Another possibility is, if you do not want CW laser action, you can employ a high power nitrogen laser or excimer laser or a third harmonic or second harmonic of neodimag laser. All these lasers can pump the dye molecule from S0 to S1 and produce laser action. Then you will have a burst of pulse laser. The pulse laser can be, the pulse width of the laser can be of the order of few nanosecond, few picosecond, few femtosecond. All these are possible by using various techniques of mode locking, Q switching, etc. That means, this particular dye solution laser are called laser scientist pipe dream. Why we call this laser scientist pipe dream is, it has all the features of being an ideal laser media. What are they? First thing, it is cheap, it can be pumped by flash lamp or it can be pumped by a laser, it can work in CW mode or a pulsed mode. Pulsed mean it can be millisecond, microsecond, nanosecond, picosecond, femtosecond. Whatever pulse width you want, you can generate from the dye solution laser. Not only that, it is highly tunable. How it is tunable? If you can look at the right side spectrum, the fluorescence spectrum for a dye like a rhodamine 6G, it starts from somewhere from 600, it goes up to 650 nanometer. That means, we can start tuning the laser action from 600, 601, 602, 603, like that we keep on continuously tuning over a range of wavelength. So, for the first time, wavelength tunable lasers were possible only with the dye solutions. You cannot get it from ruby laser, you cannot get with the neodimag laser, you cannot get this with the nitrogen laser. Most of the lasers are not wavelength tunable, whereas dye lasers are wavelength tunable. Inexpensive, the material is a water soluble dye which can be bought in any pharmacy also. Look, you can get in many of the medical shops, some of these, in some of the food stuff company can easily sell you the dye. The dye dissolved in water, dissolved in alcohol will be a laser medium, whereas a ruby rod will be about at least 1 lakh now. The dye solution medium will be about 100 rupees or 200 rupees, not more. So, it is very inexpensive. All these put together make a very fascinating, very important dye laser. I am just giving the two important design for pulse laser, pulse dye laser. If we can look at this one, you have two tubes. One tube contains dye solution. The dye keeps on flowing. The top tube contains dye solution continuously flowing. This is at the focus of a cylindrical resonator, cylindrical mirror cavity. The other focus you will have a flash lamp. Remember, this is a linear flash lamp. In we should just go back to see the ruby laser. The ruby laser has helical flash lamp. It needs very efficient pumping, lot of energy has to be put there. So, you keep on spiraling it, spiraling like a mongoose around the cobra, it can spiral and it can produce flash lamp, and then it can produce excitation. You can see the flash lamp pump dye laser design. This is entirely different from what we had for ruby laser. You have a cylindrical, in fact, an elliptical cavity with the mirrors completely coated inside. In one of the foci of ellipse, you have a tube in which dye solution is flowing continuously. This is going like this. In the another focus, you have a flash lamp. It is a linear flash lamp, not a spherical flash lamp as we had for ruby laser. This is far more efficient for this than that one. Apart from this, the flash lamp connected to a capacitor bank, connected to a high voltage of about 2000 volts or 3000 volts, will produce intense flash lamp. The light from the flash lamp will all get focused on the midpoint, the cylindrical midpoint of the dye solution. So, they will produce enormous amount of excitation, population version, which leads to spontaneous emission and stimulated emission. Then you have the two mirrors on this side, which will produce repeated training for the photons to go back and forth to produce more and more stimulated photons. Eventually, when there are sufficient number of stimulated photons inside, a part of it will come out as laser. This is the general schematic, general design of any laser. Only thing difference is, in this case, the flash lamp is a linear flash lamp, and it should be fast also. It cannot be a slow flash lamp as in the case of ruby laser. It needs a fast flash lamp because the upper energy level of dye solution is of the few nanoseconds, whereas for ruby laser it is few microsecond or even millisecond. There are certain differences. We shall mostly, the laser engineers will take care of that, all these aspects. This is an example for flash lamp pumping. Another very important, most commonly employed pumping design for dye solution laser is the nitrogen laser. This is my favorite. In fact, my PhD is in this line. We start with a nitrogen laser, which is an ultraviolet laser. You use a cylindrical lens. This cylindrical lens will make a line image on the dye solution taken in a cuvette, in a small rectangular cuvette. So, it will form a line image of about 1 centimeter length, that is all, 1 centimeter or 1.5 centimeter length. But the pumping will be very fast. The nitrogen laser puts plenty of photons in a time duration of about 10 nanosecond or even less. Since the pumping rate is very high, it will produce intense gain. It will produce intense gain because it will produce intense population version in a small length of 1 centimeter. Then again the same story, the population inverted, that 1 centimeter length will start with the spontaneous emission and stimulated emission, which will go to the reflectors. In this case, you have a diffraction grating on one side and another 100% reflecting mirror on the other side. In between, you have a partially reflecting mirror. Why we have all this one, I can explain in a minute. You can easily understand. When I pump it hard in the dye solution, you have a intense population version. The dye has a quantum yield is about 8.8. So, you get intense stimulated photons coming out both sides, and it is a broadband emission. The broadband emission will have a spectral width of about 10 nanometer. The 10 nanometer light will be going towards the grating and towards this one also, towards the 100% reflecting mirror also. then the 100% reflective mirror will specifically select 1 or 2 nanometer. This 100% reflecting mirror and also the diffraction grating will do the wavelength selection. For example, in a coumarin dye, you will get spontaneous emission and amplified spontaneous emission both in around 450 nanometer with the bandwidth of 10 nanometer. This among the 10 nanometer, the grating will choose only 1 nanometer, that will be 450 nanometer, not 451, not 452. Then that particular wavelength is fed back to the population inverted media, and then this one will go to the partially reflecting mirror, then it comes back. So, 451 nanometer stimulated photons will go back and forth few hundred times, and eventually when there are plenty of them, they will all be get reflected in the 100% reflecting mirror, which will take the wavelength, dye laser wavelength out. This is the geometry of transverse pumped nitrogen laser pumped dissolution laser. When we what do you mean by transverse pumping is, the pumping is in this direction, laser action is in this direction. So, it is transverse to each other, that is why it is called transversely pumped dissolution laser pumped by nitrogen laser. You can get laser output from the pumped or from the pulse laser also from the wavelength region of 390 nanometer to 1000 nanometer. When I say 390 nanometer, 1000 nanometer, I need to use different types of dissolution pumping with the same nitrogen laser. I can use the same nitrogen laser. If I put a coumarin dye, I will get a laser from 440 nanometer to 455 nanometer tunable. I can get 440, 440.1, 440.6, 441, 450, 450.1, whatever I want, I can get continuously tunable from 440 to 460 for coumarin dye. Suppose somebody asks, we need a laser at 580, what I need to do is, listen very carefully, all that I need to do is just use a pipette, take the coumarin dye out, pipette out, put a rhodamine dye, there will be some residual coumarin dye, keep it, because that will help to pump. So, just drop it, switch on the nitrogen laser, then immediately, I repeat, immediately you will get a laser at 590, 592, 593.6, whatever wavelength you want, you will get from the rhodamine 6G dye laser. This kind of wavelength tunability, the ease with which you can play around for different types of laser is possible only with the dissolution laser, and that is why we say it is a laser engineer's pipe dream. Well, now all this, the beam divergence is about 1 or 2 milliradian, wavelength tunable as I told you, it is about from 400 to 1000 nanometer, typical output is about 1 watt. That is all we need to know about dissolution. The main advantage of applications of dissolution laser, this is very useful for wherever you get different, wherever you need different laser, we will always use dissolution. You can, with the simple changes in the design, you can get infrared laser, visible region, near ultraviolet laser, all these are possible. Not only that, for spectroscopy we employ variety of light source. For example, in absorption or emission, we use xenon lamp, and then from the xenon lamp we put a grating, choose a particular wavelength for certain absorption or emission experiment. Remember, xenon lamp produces incoherent light. Now, for the first time, I have a tunable laser. Instead of using a flash lamp, using wavelength selection from the flash lamp, I can put a dissolution laser. I can just choose laser at 400 nanometer, 401, 402. I can mix with the rhodamine, that is, I can mix coumarin plus rhodamine. So, it will be something like a sambar mixed with it. All these we play around in a laboratory. So, I can get a laser from 400 to 600, even 700. I can add some more of cyanide dye, coumarin dye, rhodamine dye, fluorescein dye, cyanide dye, all of them we can mix it in alcohol, pump it with a nitrogen laser or excimer laser. I have a laser source tunable from 400 to 700 nanometer. That means, I have a laser in the entire wavelength. That is the most fascinating features about dissolution laser. Let us now see for next thing is about argon ion laser. A typical example for gas laser. What we have seen was the ruby laser, a solid state laser. The solid is an insulator solid. Then we saw a liquid laser, typical example being the dissolution laser. Now, we are passing on to a gas laser. The most respected gas laser anywhere in the world is argon ion laser. Why this is so respected, you will see in a few minutes. Here, the medium is an argon ion. Of course, you must have heard about these are the rare gas lasers. You have some of the very rare gases like helium, neon, argon, krypton. Like there are so many of them. Out of that, argon ion. In this case, what do we do? Just I will show you this energy design. Then immediately you can catch up, since you are already familiar with the laser. Straight look at the tube. You have a discharge tube, long discharge tube, in which you have argon gas. That is all. Usually at the level of few torque pressure. Then for gases, you cannot use optical pumping. If you use optical pumping, all the light that falls on the argon gas will be transmitted out. So, it will not light excitation. I hope you remember, to make any laser action you must have a pump source, and then earlier I had told you there are only two major pump sources: electrical discharge exclusively for gases, optical excitation exclusively for dissolutions and solid state laser like a ruby or neodymium. Now, for the first time in our discussion, we are seeing a gas laser, argon gas. This can undergo population inversion only by intense electrical discharge, and that is what is being done there. Now, once an electrical discharge is done, usually it takes 2 kV to produce a discharge and maintain the discharge, the voltage will come down. It will come down to 600 or 700 volts. That is all. The current inside will be of the order of few amperes, not few milliampere, few amperes. Whenever you have so much current, you will have plenty of argon atom, argon ion, both. Out of this, it is the argon ion which get excited from one particular energy level to another particular energy level. From there, the energy level is shown here. Yes, these are the energy level E0, E1, E3, all these represent the energy level for argon ion. When we excite argon gas, it will become from argon to argon ion. From argon ion it start producing laser action. All these things we shall see in the subsequent lecture. It is a very respect laser. We shall see the complete detail in future. Thank you very much.